Hello, today I am going to present our hybrid study using quantum computing platform Qiskit and the non-equilibrium Green's functions formalism, focusing on nanoribbon-based nanoarchitectures as resonant tunneling diodes. I am Arda Muratidis. I, Emir Çelet, and Emir Dinçel are three high school students from Robert College, Turkey, and we work together with Dr. Aydın Özcan, researcher from TÜBİTAK, on this research for about 1.5 months as our summer project. So first of all, I am going to give you a brief introduction of our project. Then I will talk about the thermalization, many-body localization of graphene nanoribbon edges. Then I will talk about the resonant tunneling diode behavior, and then I will conclude. So one of the main motivations for our research was inspecting the resonant tunneling diode behavior. In resonant tunneling diodes, electrons are able to skip through resonant states at specific energy levels. And the behavior is characterized by a negative differential resistance, where if you plot the current versus voltage graph for a resonant tunneling diode, you get an interval where the slope of the graph is negative, as you can see here. This leads to quick and low power electron transmission, increasing the efficiency of many low power electronics, such as oscillators in circuits, frequency dividers, and analog to digital converters. Another motivation for our research was working with graphene nanoribbons. Graphene is the two-dimensional allotrope of carbon, which Andrei Geim and Konstantin Novoselov were awarded the Nobel Prize in Physics in 2010 for their work on extracting it from the three-dimensional allotrope graphite. Graphene nanoribbons are quasi-one-dimensional strips of graphene which have electronic properties that are largely dependent on their structural parameters, such as width and edge orientation. Speaking of edge orientation, graphene nanoribbons are divided into two main groups according to their edge orientation: zigzag and armchair, as you can see in the image on the right. While it is known that the bulks of graphene nanoribbons are thermalized, it is usually assumed that the edges are also thermalized. However, in this research, we also aim to show that the edges are thermalized. So now, let's talk a bit about thermalized versus many-body localized states. In thermalized systems, the system effectively reaches thermal equilibrium if given an ample amount of time. Electrons are able to move freely throughout the structure, and that allows conduction. There is also a loss of information about the initial state, since any thermalized system, regardless of the initial configuration, will evolve into a state of uniform particle density. It is impossible to predict the initial state by looking at the final state. On the other hand, in localized systems, the wave functions of the electrons are localized. That means that outside of the region of localization, the wave function decreases exponentially. That goes to show that the electron has a really low probability of being found outside its region of localization. We say that electrons are confined to certain regions within the system, and that impedes conduction. Finally, if in a system there are electron-electron interactions, we say that the system is an interacting system. And if an interacting system is localized, then it is said to be in a state of many-body localization. In our research, we aim to simulate the edge structures of graphene nanoribbons using IBM's quantum computing platform Qiskit. There, we utilize the trotterized quantum circuit from Ruihao Lee's research in order to evolve the system through time to see if it evolves into a state of uniform particle density or not. After showing that the edges of graphene nanoribbons are also thermalized, we inspect the Aronow-Bohm ring as a suggested topology by Motohiko Ezawa as a candidate for a resonant tunneling diode. There, we utilize the non-equilibrium Green's functions formalism to plot the current versus voltage curve for the Aronow-Bohm ring to see if it indeed demonstrates the negative differential resistance promised by the behavior. As you can see in the image, it is especially important to study the edges in the context of the Aronow-Bohm ring because the structure doesn't have a bulk. It only consists of edges. So now, let's talk about the thermalization, many-body localization of graphene nanoribbon edges. In order to accurately simulate this structure, we must make some changes to the Hamiltonian of the system. We must account for the edge effects such as hydrogen passivation. Hydrogen passivation is when hydrogen atoms bond with the dangling bonds of the carbon atoms at the edges of graphene nanoribbons, and it results in a higher electron density on the edges compared to the bulk. This is also suggested by observations using scanning tunneling microscopes. In order to account for the higher electron density, we must incorporate the negative on-site potential, and that leads to a non-zero on-site term, which is the epsilon term in the Hamiltonian below. Also, in an interacting system, an excited electron may decay into a lower energy state and give its energy to the surrounding electrons and potentially incite their delocalization. Therefore, we must also add an interaction term which accounts for the electron-electron interactions, and that is the U term in the Hamiltonian below, and it's also called the Hubbard correction term. Then, we must express our Hamiltonian in terms of the Pauli gates. Previously, the Hamiltonian of the system was in the second quantization formalism only expressed in terms of the creation and annihilation operators. The creation and annihilation operators may be written in terms of the Pauli gates, as shown here. And then, if we just plug in the expressions, the transformed Hamiltonian of our system becomes as follows. Then we evolve the system through time using the trotterized quantum circuit. The trotterized quantum circuit discretizes the time evolution into small steps of 0.15 time units. We utilized 9, 12, and 15 qubit circuits in order to show that the qubit size doesn't alter whether our system turns out to be thermalized or many-body localized. We also put 3 Pauli X gates at qubits 0, 4, and 8 in order to account for the particle excitations. The Pauli X gate switches the initial state of the qubits from state 0 to state 1, and state 1 corresponds to an excited state. The quantity we use in order to deduce if the particle density of our system is uniform or not is the system imbalance. The system imbalance is calculated according to this formula, where n subscript e is the number of particles at even numbered sites, and n subscript o is the number of particles at odd numbered sites. As you can see, the system imbalance suggests whether the particles prefer even or odd numbered sites, and a close to zero imbalance would indicate a roughly uniform particle density, hence a thermalized system. Here is a 6 qubit trotterized quantum circuit. We utilized 9, 12, and 15 qubit circuits. However, the structure is essentially the same. And here are our results. We plotted contour maps of average imbalances for various different values of interaction strength U and on-site potential epsilon. And we found that for the values associated with graphene nanoribbons, which are U equals 1J and epsilon equals negative 0.03J, where J equals 2.65 electron volts, the system roughly corresponds to around here, which is yellowish green, which indicates a roughly zero system imbalance. Hence, we have showed that the edges of graphene nanoribbons are thermalized. We also plotted the system imbalance over time for U equals 1J and for various different epsilon values, and we found out that for epsilon equals negative 0.01J and negative 0.05J, the system imbalance converges to zero as the system evolves through time. However, for epsilon values with larger magnitude, the system imbalance clearly deviates away from zero. Now that we have showed that the edges of graphene nanoribbons are thermalized, we will omit the on-site potential and the Hubbard correction term, and we will only focus on the side-to-side hopping term in our Hamiltonian. Now, let's talk about the resonant tunneling diode behavior. We are searching for a topology that yields the negative differential resistance promised by the behavior, and for that purpose we inspect the Aharonov-Bohm ring. We put 2 ports at each side of the Aharonov-Bohm ring in order to assure that current flows from one end of the system to the other. In order to plot the current versus voltage curve for the structure, we utilized the non-equilibrium Green's functions formalism, which is used for the exploration of transport properties of systems and calculates the response of a system to a constant perturbation. Here, you can see the retarded Green's function, where I is the identity matrix, and sigma source and sigma drain are the self-energy matrices for the source and the drain respectively. And the -1 exponent symbolizes the taking inverse of a matrix. And the advanced Green's function is simply the Hermitian adjoint of the retarded Green's function. Then, the broadening matrices can be given in terms of the self-energy matrices, where I is the imaginary unit. Then, we can calculate the transmission function, which is related to the probability of an electron transmitting from one end of the system to the other. Here, Tr is the trace operation. Finally, the current through the system can be obtained according to the following formula, where E is the elementary charge, H is the Planck's constant, and F source and F drain are the Fermi-Dirac distribution functions for the source and the drain respectively. And here is our code that calculates the current through the system, and it essentially does the same math as I showed you just now. You can also find our GitHub link down below. And here is our results. As you can clearly see, there is the negative differential resistance region, roughly between 0.20 volts and 1.20 volts. Hence, we can come to the conclusion that the Aharonov-Bohm ring can be used as a resonant tunneling diode. Now, let's conclude. In our research, we first simulated the edge structures of graphene nanoribbons via Qiskit to see if they were thermalized or many-body localized. There, we made some changes to the Hamiltonian in order to account for the edge effects and the electron-electron interactions. Then, we propagated the system through time and measured imbalance to see if it evolved into a state of uniform particle density or not. We found a close to zero imbalance value, which indicated that the system evolved into a state of uniform particle density and hence was thermalized. After showing that the edges are thermalized, we inspected the electronic properties of the Aharonov-Bohm ring. There, we used the tight binding Hamiltonian in the second quantization formalism, only focusing on the side-to-side hopping term. We utilized the non-equilibrium Green's functions formalism in order to plot the current versus voltage curve for the Aharonov-Bohm ring, and we found that there was the negative differential resistance region promised by the resonant tunneling diode behavior, and hence we came to the conclusion that the Aharonov-Bohm ring can indeed be used as a resonant tunneling diode. Thank you for listening.